Good afternoon.
Firstly, I am introducing you, and obviously this will be coming to the webinar. Sir H.K.D. Bhadesia is also popularly known as Professor Harry Bhadeshia. He is a physical metallurgist and Tata Steel Professor of Metallurgy at the University of Cambridge. He did his PhD degree in 1979 under the guidance of Professor David Edmonds with the title of the thesis, The Significance of Ferrite and Austenite in Steels. Professor Bhadesia has phase transformations and complex properties research group at the University of Cambridge, where a lot of students, your master degree students, PhD students, and a lot of researchers are also working there. His area of interest includes metallurgy, phase transformation in steel, computational modeling, neural network, Baynite, etc. He is the author or co-author of more than 650 published papers in the field of metallurgy and several books like Baynite in Steels, Microstructure and Properties, Geometry of Crystals, Polycrystals and Phase Transformation, etc. During 2005 to 2018, as the founding director of the Computational Metallurgy Laboratory, he helped to create the Graduate Institute of Ferrous Technology (GIFT) at POSTECH, University of Science and Technology in South Korea. I was fortunate to mention that I got this opportunity to work under Professor Bhadesia for 1 year from July 2007 to July 2008 in CML, GIFT POSTECH, to work as a postdoctoral researcher. And I have gained a lot of experience under his supervision. So I am really fortunate, and I must mention this occasion. He established and took the lead of the new ESCAPE University Technology Center between ESCAPE and the University of Cambridge to conduct research in the field of physical metallurgy of bearing steels over the period 2009 to 2019. He has developed a wide range of freely accessible teaching materials on metallurgy and associated subjects. The subject matters cover crystallography, metals and alloys, steels in particular, phase transformation theory, thermodynamics, kinetics, mathematical modeling in material science, information theory, process modeling, thermal analysis, ethics and natural philosophy. Professor Bhadesia has served as editor of the journals like Material Science and Engineering A, Material Science and Technology, Science and Technology of Welding and Joining. He is the recipient of a lot of awards and honors like Hume Literary Prize, Royal Society Armours and Brasiers Company Prize. He is also a Fellow of the Royal Society. He is also the Fellow of the Royal Academy of Engineering. He is also the Honorary Member of the Iron and Steel Institute of Japan. He is the Fellow of the Institute of Materials, Minerals and Mining. He has also conferred Knight Bachelor in the Queen's Birthday Honours. Okay. So with this introduction, I am welcoming Professor Bhadesia in our webinar series, and request you to deliver his talk in this occasion.
Thank you. Thank you very much indeed, Professor. I'm very grateful for those comments, but I'm more grateful for actually being given this opportunity to present at your 80th anniversary, which is a remarkable anniversary, and I'll come back to that later. The slide that you see here is actually steel, which have been produced in Switzerland, and that's why you have the enormous amount of snow and so forth. And what I want to show you today is a few of the developments over the last 50 years in steels. And you know, these developments are very frequent, so I can only use selected examples But if we go to the next slide, could you change to the next slide, please?
I am trying, sir, but it's not moving actually. Let me try.
Yeah, I can see it now. And if you put it on full screen. Okay, so before I mention the more recent developments, by far the largest development in steel was in the 1960s, early 1960s in Sheffield, where microalloying steels were invented by these characters. So we have Terry Gladman on the left, and we have Irwin, Pickering, Irani, and Bob Morrison. And these people invented a concept at a time when there was no industry for niobium. Okay? And they created the industry for niobium by showing that a very small concentration of a microalloying addition can dramatically change the combination of strength and toughness in steels. And there are now approximately 40 billion tons of steels which are microalloyed in routine use, and they are so good that they do not fail, and therefore the public doesn't know about them. But if you go to the next slide, okay, this is a bit of a pain.
I don't know why it's not moving during the presentation mode. Can you? Yeah, it's moving. It's fine now.
So can you move to the next slide? Yeah. So this particular discovery of microalloyed steels, in my opinion, and I wrote this down in one of my books, that it really should have won a Nobel Prize. Because if you look at many of the Nobel Prizes that we get nowadays, they don't actually create something which influences the lives of so many people. Whereas the microalloying steel concept really changed the quality of life for a very large number of people in a very big way and completely reliably. Okay, the next slide. Now, I'll go into a few examples. So just when people think that steels have run out of ideas, this particular concept came about. These are the twinning induced plasticity steels, where you start off with quite a small strength of the order of 300 megapascals, and then there is a work hardening mechanism which leads to a strength in excess of 1 gigapascals and an elongation of 60%. That is really quite remarkable. Okay, so an elongation of 60% and a strength of about 1.2 gigapascals. So the mechanism of this work hardening is interesting. The steel contains a very large amount of manganese, and therefore it is a fully austenitic steel. And it starts off deformation by mechanical twinning. So here you see a transmission electron micrograph showing you extremely fine mechanical twins. This scale bar here is 1 micrometer. And what happens is that just as when we refine the grain size, we get a greater strength, these twins partition the austenite into smaller and smaller compartments as deformation happens. and therefore they produce strengthening by dynamically refining the grain size. So we call this a dynamic hole patch effect, where the islands of austenite are divided into smaller and smaller sections by these twins. Okay, so this is the TWIP steel concept. And if we go to the next slide, the properties are really quite amazing. So on this plot, we are plotting the impact toughness versus temperature, and you can see that there is no ductile brittle transition temperature, and even at minus 196 degrees centigrade, it has a toughness of about 100 joules on a standard Charpy, notched Charpy test. Furthermore, it has a lower density than a normal steel. It's about 7.3 grams per centimeter cubed as opposed to 7 grams per centimeter cubed because of the addition of silicon and aluminium. It's fully austenitic, and even at very high strain rates, it behaves very well. In other words, it maintains its good toughness and elongation at very high strain rates. So if you go to the next slide, this is a movie that I obtained from Warwick University. And what this is you take a square-sectioned material. On the right-hand side, you have steel. On the left-hand side, you have composite. And do a crash test. So these are the sort of elements that go into cars, so that when you have a frontal impact, when you have a frontal impact, basically the deformation absorbs energy. On the left-hand side, when the composite fractures, it's because the interfaces are being broken, and that is the mechanism of energy absorption. On the right-hand side is plastic deformation. Go to the next slide. So this is a similar test done by making this crash element out of TWIP steels. And you can see that it's deformed quite a lot. However, there is a problem. Because the deformation starts off at a low stress and then builds up to a very high stress, you only absorb energy at the corners of these concatenations. It doesn't absorb energy uniformly because it's only the edges of these zigzags that have been deformed sufficiently to reach a high stress in this stress-strain curve. So it actually fails to serve properly in a crash scenario. Now, there's not a great deal you can do to change this stress-strain behavior. You can actually introduce precipitation hardening, which will increase the initial strength level, but other properties change at the same time. So there is an engineering solution, a very clever engineering solution that emerged in Germany, whereby you can make a TWIP steel uniformly absorb a great deal of energy, not just at the corners of this. So if you go to the next slide. Now this is a movie. The cylindrical elements that you see in the middle are made from TWIP steel. And the idea is that when you get compartments of trains colliding, the cylindrical component is extruded through a die, and therefore you put uniform deformation all across your component. I don't know whether you can play the movie or not. Okay, if not, we can continue. So basically, there's an engineering solution as opposed to a material solution that allows a TWIP steel to absorb a great deal of energy during deformation. So we can move on to the next slide. Okay, so this is showing the extrusion of the cylindrical component, and this is an actual crash test. Okay. So you can see those cylindrical elements which are made from trip steels, they are actually being extruded into much smaller diameter during the crash. And that is giving uniform deformation, and therefore you exploit all of the stress strain curve of the trip steel. Okay, next slide. Now this is an interesting picture where we have both ferrite and austenite. The ferrite is baynitic ferrite, very, very thin plates of baynitic ferrite. You can see the scale marker there. They're about 1/4 of a micrometer thick. And the austenite is retained simply by the partitioning of carbon. Okay, so it's an extremely cheap form of austenite. Carbon is very cheap. And what we have is a beautiful composite of ferrite with austenite in between. And you've already seen that austenite does not have a ductile brittle transition temperature, so it's very good for toughness, whereas the very fine plates of baynite, which are a consequence of the mechanism of transformation, provide strength. And this particular microstructure, in which we have no carbides at all, because quite a lot of silicon has been added to the steel, and silicon retards the formation of cementite. This concept has found applications in a very large number of scenarios, and I will just mention 2 of them. But before I go on to mention the application, I want to show you a movie which explains why these plates are extremely thin. So if you go to the next slide. If I take a sample of austenite and I polish it completely flat, and then I allow it to transform into baynite, then you can see that it produces quite severe deformations, right? And these deformations have a special characteristics that they involve a very large shear deformation. And in order to minimize the strain energy associated with the shear deformation, the baynite plates form as very thin plates compared with martensite, for example. So martensite plates will generally grow all across an austenite grain, and therefore they tend to be coarser. So these plates are only 1/4 of a micrometer in thickness. So, just imagine you can get grain refinement to 1/4 of a micrometer without any imposed deformation. So processes like equiangle extrusion and severe plastic deformation are not terribly useful when it comes to making a commercial steel, because they focus on very small quantities of material. And here we are getting a grain refinement to 1/4 micrometer size simply because of the mechanism of transformation. If you go to the next slide. So this is a Swiss steel. We had a collaboration with them to work on this mixture of baynitic ferrite and austenite. And this is an actual component for fuel injection, okay, made from the baynitic steels, because you can engineer the properties. You can vary the thickness of the baynitic plate. You can vary the retained austenite content. So it basically opens up opportunities for very many applications. And if you see the next picture, this is this is another actual component which is made from this combination of baynitic ferrite and austenite. And I think if you click to the next slide, people think of cast irons as being very brittle materials, right? And that is true if you have flakes of graphite and lots of cementite and so forth. But the same concept of a mixture of austenite and baynitic ferrite has been extended to cast irons as well. So we need to go to the next slide. So here you see what's known as Ostemper ductile iron. So there's a large lump of graphite there, but the matrix has been transformed essentially into a mixture of baynitic ferrite and austenite. And this cast iron, okay, remember this is cast iron. It has a toughness of 120 joules at room temperature and a strength in excess of 1100 megapascals. So this has opened up many opportunities to make complex components simply by casting such as the component illustrated underneath. Now, I said to you earlier on that this mixture of bayonitic ferrite and austenite can be controlled. The various parameters that define the microstructure can be controlled very easily by altering the alloy chemistry or by altering the transformation temperature. And there's so much understood about this that you can actually do calculations. You don't need to do trial and error experiments to redesign the scale of the structure. So if you go to the next slide, this is the world's first bulk nanostructured material. It can be produced in thousands of tons, and it consists of these bayonitic ferrite plates, which are only 20 nanometers in thickness, and they are actually finer. They are actually finer than the carbon nanotube that you see on the top right-hand side. Okay. Could somebody stop this?
Gamma, alpha, beta.
Sir, should I move to the next slide?
The next slide shows a component that is made using this structure, this nanostructure. So this is a very large bearing. Okay. So for wind turbines, you have a 4-meter diameter bearing. The rolling elements in this bearing are made from the bulk nanostructured steel. The ring is too large at the moment with the facilities available to make from this nanostructured baynite, but in the background you can see smaller bearings. And I'm told that one of those bearings has a ring which is made from nanostructured baynite. Okay? So this concept has now actually been applied to one of the most critical components that you have, because wind turbines these days are really huge. The scale is enormous because the larger the wind turbine, the less is the cost per unit of electricity, and the more you capture the wind. So there are concepts in which bulk nanostructured baynite is now being applied, but there is a problem. If you go to the next slide, and it's a very major problem, that you cannot weld it, right? Because it contains about 1 weight % carbon. So whenever you weld it, you will spontaneously get cracking. Okay. So how do we solve this problem? We want an extremely strong steel, which at the same time has a reasonable carbon concentration, and yet we should be able to manufacture it in very large quantities. Okay. So bayonitic transformation is not going to do that. It's got to be weldable. That means we've got to go to lower carbon concentration, and the nanostructured baynite can only be produced at a sufficiently low temperature by adding loss of carbon. So we have to think differently. So if you go to the next slide, this is showing Martenssite plates, okay? And the Martenssite plates are in high carbon austenite, so you can see that they're periodically cracked. Now, the idea is, supposing you make the austenite grain size smaller than the distance between these cracks, because these cracks happen when you're able to transfer stress onto the Martenssite plates. But if you make the Martenssite plates very fine, smaller than the distance between, then they will not crack easily under stress. Okay, so what we need to do is to get the austenite grain size to something of the order of 1/4 of a micrometer. Now, how on earth can you get an austenite grain size in a mass-produced material, which will have a reasonably low carbon concentration, yet have a strength of 2 gigapascals and be weldable? So if you go to the next slide, we can microalloy the steel with vanadium carbides. Why with vanadium carbides rather than niobium carbides? Because we want a finish rolling temperature that is very low. Okay, and niobium carbides generally precipitate at a high temperature when you have a high carbon concentration. So here we are talking about 0.38% carbon, and niobium carbides would be lost before the finish rolling temperature. So what we want to do is we want to pancake the austenite grains so severely that the effective grain size becomes incredibly small. Okay, so if you go to the next slide, shows the beautiful structure obtained at Tata Steel in India of severely pancaked austenite grains. Okay, now not only are they severely pancaked, but there are lots and lots of deformation bands within each of those pancaked austenite grains. So what that means is that you've reduced the grain size dramatically. And just to show you the effect, if you go to the next slide, these are EBST figures from a single austenite grain. On the left-hand side, the grain is undeformed. On the right-hand side, it is deformed and then transformed into martensite. So what we've done is we've broken up the martensite into very small regions in what should be a single crystal of austenite, but there are severe orientation gradients inside each austenite grain, and therefore we have broken up the 24 variants that you normally get in a single austenite grain to thousands of variants, which are misoriented with respect to each other. Okay, so the next slide. This turns out to be a really remarkable material. So there's no problem at all with welding it, right? Even though it contains 0.34% carbon. This is arc welding. Laser welding has been tried, but it's not a practical tool for making structural components. And if you look at the toughness, and the crosses there are for nanostructured Baynite, and the new material here systematically has a toughness of about 75 megapascal root meters. And if you look at the Charpy results at minus 40 degrees centigrade, you've got impressive Charpy results and elongation. Now, generally when an alloy is developed in a university, we start to make claims before they are justified, okay? So this has a strength of the order of 2 gigapascals. And one of the applications that we've been looking at is armor. So let's go to the next slide. And there is a movie there. So this armor is different. So we want ballistic resistance, but we also want blast resistance. So we test this by firing at a very high speed an aluminum foil against a sheet of steel. And you can see that this steel does not break under that impact. So it can serve the dual purpose of blast resistance and ballistic resistance. But you really want to think of more than just defense applications. So if you go to the next slide, the next slide will show you a very severe wear test. So the thing that's rotating around is steel samples which are hitting granite. And this is at a very high speed. This is a slowed down version of the movie. And basically, this is a very severe test where we get both impact and abrasion. And this material proves itself to be better than anything that is commercially available. If you go to the next slide. So the red dot there is straight out of the rolling mill, okay? And you can see that it has outstanding wear resistance compared with anything else that is available. So how do we go from a laboratory test where we are, rotating steel in a tumbler containing granite, which may not be representative of real life, to a real life test. So if you go to the next slide, this is a beautiful image from Tata Steel in Jamshedpur. On the left-hand side, this is the material they've been using for many years, where minerals impact on the steel, and the steel is coated with an expensive, hard-facing alloy. Okay, it's a very chromium-rich alloy. And you can see that within 3 months, there is a huge loss of material, and it has to be replaced. So what we did was we removed this, and we placed the new material, which is extremely cheap compared with this. It has no coating. So go on to the next slide. And it has performed for a year without any perceptible damage. Okay, so it's much cheaper than the coated steel that has been used for many years. And so far, there is no damage. And we don't, we are waiting for it to be damaged so that we can study how the damage happens. But it hasn't happened yet. And this is in a real plant application. And Tata Steel has now started to put this material in different parts of their factory, where different mechanisms of wear operate. So we shall see in a few years' time how this performs. And there is a plan to set up a small industry based on this. Okay, can we go to the next slide? Now, there are many people in the world who are working on hydrogen, but if you look at this paper, which was published in 1875, hydrogen embrittlement, okay? This was the very first paper ever on hydrogen embrittlement, because Johnson was trying to clean steel by putting into acid, and discovered that afterwards the steel became very brittle, but if you left it for several days, then it would recover its properties. And 90% of everything that we know about hydrogen embrittlement was already in this paper, which was about 30 or 40 pages long, but very systematic work, okay, and in 1875. So we know more or less the science of hydrogen embrittlement, although it is not a quantitative science. And my feeling is now the focus has to change to prevention of hydrogen embrittlement. So if you go to the next slide, this is some work that we did with Nippon Steel, where we introduced very fine carbide particles whose lattice parameters are controlled so that there's a strain field around the particles, and that attracts hydrogen atoms, because Johnson proved that actually it is diffusible hydrogen that does damage. Okay, so if you stop it from diffusing, then it cannot do damage, because the concentrations are remarkably small, like less than 1 part per million of hydrogen, and it's inconceivable how less than 1 part per million can actually do damage to the steel. But what happens is that when you get a crack, there's a stress field around the crack, and the hydrogen migrates towards that, so its concentration, effective concentration, is greatly increased in the region which is subjected to the worst circumstances, and therefore you get embrittlement. So if you introduce hydrogen traps inside your material, then you stop it from diffusing and you improve the properties. And the graph shows you that, with appropriate heat treatment, we can trap something like 10 parts per million of hydrogen at these traps. So if you go to the next slide, I want you to remember that to make an actual component, you never focus on just one property. So British Petroleum wanted to create a steel for undersea applications, which would be resistant to hydrogen, but would also meet all of these criteria. Okay, so the engineers, when we started the project, the engineers told us that all of these criteria must be met. And this is quite a long story, but to cut a long story short, if you go to the next slide, we designed a steel which meets all of those properties. So this is the normal commercial steel that BP uses. And this was the material that we created, which is higher strength and yet maintains the toughness. And there was something called a stretch target. That means how far can we go beyond this one? And remember, it's weldable, it's got to be manufacturable in very large quantities and so forth. And you can see that we have achieved, this is the target for toughness, okay? We can achieve much higher strength, and very severe testing has been done on the hydrogen susceptibility of this material, which relies on these hydrogen traps. And we are at a stage where there will be manufacturing of a large amount of the steel. We still need a collaborator to actually make the components, because these components weigh tons. So this looks promising on every indicator that you would like. And we have a steel company which would make the material. And there are negotiations to work with a forging company to actually produce the component. And until you've done a component level test, you can't actually claim that you have achieved success. Okay. Now, I've shown you examples where steel design can lead to really interesting practical applications. The next slide, I'm going to show you some fundamental results. So this is the mechanism of the Baynite transformation on the left. The plate forms like martensite, it then partitions carbon, and then you get cementite precipitation. You can suppress the cementite precipitation by adding silicon or aluminum. And the phase diagram on the right shows that the solubility of carbon in ferrite that is in equilibrium with austenite is incredibly small. You know, the maximum is about 0.028%. So this is just a part of the equilibrium iron carbon phase diagram. Next slide. These are experiments I did back in 1981 with Bob Wall, where we used the atom probe, and the image of the bottom right-hand side shows the carbon atom segregated into the austenite, and the ferrite has lost much of its carbon. But if you do a lot of experiments, you find that actually the concentration of carbon in the ferrite is very high, okay? And we assumed back in 1981 that this was because it was trapped at dislocations. And since 1981, the instruments have become more sophisticated. So if we go to the next slide. This is Francisca, who did this work. And using the more sophisticated instruments, you can see the segregation to dislocations in the ferrite, but you can also see large concentrations of carbon which are in solid solution inside the baynitic ferrite. So when I say large concentrations, is up to 0.38%. Now, why would it remain there, even though we are holding at the transformation temperature for 10 days? Why does it remain there? Okay. Recently, there was a paper published in one of the Nature journals saying it must be because the carbon is trapped at vacancies. But you can do a very simple calculation to show that the fraction of carbon atoms that are trapped at vacancies will be incredibly small. Right? So there has to be another reason why the carbon. There has to be another reason why the carbon remains inside the ferrite, even though you give it every opportunity to partition. So the idea that occurred to me was, if you introduce carbon in ferrite, then the ferrite will be tetragonal. Okay? So we should not think about equilibrium between body-centered cubic ferrite and austenite, but rather equilibrium between tetragonal ferrite and austenite. So I got my colleagues in South Korea to do first principles calculations. And if you go to the next slide, please. So these are calculations of a phase diagram between tetragonal ferrite and austenite. And now you can see that the solubility of the ferrite increases dramatically when it's tetragonal. And we did a lot of experiments, and others have repeated these experiments to show, yes, indeed, the ferrite. Yes, indeed, the ferrite is tetragonal. Okay. Okay. So my final slide. So I want to say something about your lovely university, which is now the Indian Institute of Engineering, Science and Technology in Shibpur. And although we are celebrating the 80th anniversary, actually the university's origins are much, much older. So in 1856, it started off as a government college, then became the Bengal Engineering College, one of the first, or maybe the first engineering college in India, Shibpur. They removed the name Shibpur for some reason in 1921, and in 2004 it became the Engineering and Science University, and now it is an esteemed institute of Indian Institute of Engineering, Science and Technology. Now, when we try and create a university, people often think that it's the amount of money that the university has which matters. But actually, it's all the students that have been taught since 1856 that really is the human output, which matters more than anything else. So I want to congratulate you on your very long history, and certainly for 80 years in materials or metallurgy. And I hope this continues for many more centuries. So thank you very much. I have finished.
Thank you very much, sir. Thank you, sir, for such a wonderful session and presentation. Sir, if you don't mind, our curious attendees would like to pose a few questions. Is that fine with you, sir?
Yes, of course.
Of course. Now over to Ritam, please.
Hello, sir.
Hello.
We have a question here, like, sir, how can we like physical metallurgy subject, or how to fall in love with the subject?
Yeah, I think falling in love in any aspect of life is not something that can be taught. Okay, so you have to really be sparked by something that you're interested in, and the way to be sparked is by doing lots of reading and studying. There's no substitute for that. I hope that is a reasonable answer for your question, okay?
Yes, sir. And there is also another question, like, what is your most memorable memory about BE College?
Oh, my most memorable was the conference on neural networks and genetic algorithms, which, and the thing that I remember most, and I mentioned it to many people after I returned, is in this conference there were some really, really bright people from BESU, as it was known, and a lot of them were actually women professors. More women professors than in Cambridge University, I thought at the time. Okay, so I don't know what it is, but the university has identified clever people irrespective of gender, and that is what I remember the most.
Okay, sir. Thank you, sir.
Okay.
Thank you, sir. Team Reminiscence is grateful to you for your time and consideration. We look forward to more such exceptional talks from your side. Thank you once more for such an exhilarating journey across the development and the production of steel. Thank you, sir, for joining us. Thank you very much.
Bye-bye.
Bye.